Welcome to this short presentation on uh, Little's Law. Uh, this video is a part of our group project in the course Operations Analysis at IIT Bombay. First, let us see an overview of Little's Law. Let us see some historical background. This law was first published in 1954 uh, without a proof, and it was first published by Philip M. Morse as a simple equation L is equal to lambda W, where he challenged the readers to find a situation where a relationship did not hold. But later, John Little published a proof in 1961 showing that no such situation existed, and he is currently working as an institute professor at MIT. Little's proof was followed by a simpler version by Joel Scheller. Uh, Scheller published a different and more intuitive proof in 1972. Uh, Now let us introduce some facts about the Little's Law. So Little's Law establishes a relationship between average waiting time and average number of items waiting for a service with the average rate of arrival in a service system. It majorly deals with queuing systems where discrete items arrive at some rate in a system and they receive some service and leave. So some arrivals come, they are fed into a queuing system which provides some service to them, and there are departures. So those items wait for some time, receive some service, and then they leave. That is a basic structure of a queuing system which the Little's Law tries to model. Now let us see the formal definition of the Little's Law. Little's Law is defined as L is equal to lambda W. L is the average number of items in the queuing system. Lambda is the average number of items arriving per unit time. W is the average waiting time in the queuing system for an item. The above equation assumes that there is a steady state reached by the queuing system, and under only those conditions, this law is valid. There are some other equivalent definitions of the Little's Law, such as given on this slide, where we can represent various factors like average number in system with average arrival rate into average time in the system, which can also be represented as average number in system is equal to average departure rate into average time in the system. Average inventory can also be modeled as average throughput rate times the average flow time, and average WIP, that is work in process, can also be modeled as average throughput rate into average cycle time. Here the system stand. Now next, let us see the proof of the Little's Law with the picture. So on the right, we can see a figure where in a time period T, different arrivals and departures are happening in a queuing system. So first we can model some basic quantities with these set of equations. That is, capital T is a long period of time. Small n t is the number of items in the queuing system at time step small t. A of t is the area under the curve of nt over the time period capital T, and capital N of t is the number of arrivals in the time period t. Now using this data and by deducing the data in the graph, we can say that we can define a quantity lambda of capital T as capital N of t divided by t as the arrival rate during the time period t. Capital L of t can be defined as capital A of t divided by capital T, which represents the average queue length during time period t, and W of t as the ratio of capital A of t and capital N of t. And this represents the average waiting time in the system per arrival during t. And with a slight manipulation, we can finally represent L of t as a product of lambda of t into W of t. Now, by doing some further mathematical manipulations, we can show in the limiting case, as t tends to infinity, the terms saturate to a constant value, which gives us the final equation of L is equal to lambda into capital W, which completes the proof of the Little's law. Next, let us see some applications of the Little's law.
Okay, so now I'll talk about the applications of Little's law. So, slide, next slide. Yeah. So, firstly, I'll talk about the usefulness of Little's law in various sectors. Now, for example, it can be used for estimating the waiting times in a queue, and that can be useful for many areas, like for restaurants, if we want to estimate the waiting times for the people waiting in a queue. And it can also be used for finding the planned inventory time, that is the time after which we want to order our inventory. And next, we can also use it for the process of work in progress reduction, and that can be used in operations management. And it has also applications in product development, and another application can be found in multitasking. So yeah, next nextly, I'll give an example of an application of Little's law in fluid mechanics. So as we can see from the picture, the arrival rate of water or any liquid in a tank or a vessel is, let's say, 10 gallons per minute, and the departure rate is also the same. And in the from the figure, we can see that the work in progress, that is the quantity of water or liquid that is currently being in process, is 1000 gallons. So if we want to find the average throughput time, that is the time some amount of water undergoes the processing in a tank, we can use Little's law for that, and that is given by W equals L by lambda, where L would be the average inventory, which is 1000 gallons, and lambda would be the average arrival rate, which is 10 gallons per minute. So using putting those values, we can get the average throughput time as 100 minutes. So nextly, I'll talk about the application of Little's law in communication networks. So suppose we have a data communication system with three transmission lines, or you can say three routing routers. So, and we are given that the packets arrive at the three different nodes with different arrival rates. Let's say 190 packets per second, 300 packets per second, and 10 packets per second. And we are also given that there are about 50,000 same sized packets floating in this system. Now we want to find the average delay per packet in the system. So again, we can use Little's law, and here the for applying the Little's law, the L we use would be the average number of packets in the system, which is 50,000, and the total arrival rate to the nodes would be the sum of A1 plus A2 plus A3, which is 500 packets per second. And then applying Little's law, we can find that the average delay per packet in the system, W, would be given by W equals L by lambda, which is 50,000 divided by 500, and which we get to be 100 seconds. And this can be useful for modeling the communication system, and yeah, taking care of various factors which depend upon the average delay. Nextly, now I'll talk about the application of Little's law in a balanced assembly line. So suppose from the figure we can see that there are five machines in the assembly line named A, B, C, D, and E, and we are given that the processing time of each machine is 3 minutes per unit, and which is equivalent to it producing 20 units in 1 hour. So now suppose we want to apply Little's law. So here the throughput of the whole assembly line is 20 units per hour, as each machine is producing 20 units per hour, and the lead time or the W we use in Little's law is 15 minutes, as each machine takes 3 minutes, and there are 5 machines, so overall 1 unit would take 15 minutes to be get processed. And so here, if we find out the work in progress, that is the number of products in undergoing processing at a given time, it would be 5 units. As and we can also see that there are 5 machines and each machine would have 1 unit, that would give 5 units. And we can also use Little's law, that the work in progress is equal to the lead time into throughput. And if we convert the units, the convert the both the quantities in the same unit, we get the work in progress as 5 units, which is the same as we can find intuitively. So nextly, now let's look at some examples.
So, as we have seen that the Little's law is applicable in many environments, including the manufacturing and service industries. We'll now let us take a look at few more examples in more detail. So, in this hospital ward example, we wish to determine the size at the staffing level for maternity ward. And from the historical data, we know that the birth rate for a local community is 5 births per day. And an average, a woman stays in the ward for 2.5 days. Therefore, we can use Little's law here to predict the average number of mothers in the maternity ward. And the average arrival process corresponds to the women arriving to deliver their babies. And the arrival rate A here is 5 births per day. Therefore, we know that W is equal to 2.5, and therefore L is equal to lambda into W, which gives us 12.5. However, the law here only provides the average requirements, and we would need to design a maternity ward to accommodate its peak requirements. For instance, we would certainly want more than 12.13 or 12.5 or 13 beds in order to handle the variability in the occupancy of the ward. So one needs to use the queuing models or the simulation in order to explore the trade-off between the utilization of the bed. Nevertheless, the Little's law provides a starting point for investigation since we know the average number of beds that are needed. So the next example is that of the toll booth, where we want to estimate the waiting time for vehicles. Here we are using the Little's law to ask what quality of service is being delivered in terms of averaging waiting time per vehicle. So the arrival rate to the toll booth is 3,600 vehicles per hour, and the expected number of vehicles in a system is 20 vehicles. Therefore, on an average, the time a vehicle spends to the toll booth is W equal to 20 by 3,600, which is 20 seconds. Next slide. Now, talking in terms of the robustness and generality of the Little's law, it's being used under systems which are the steady state assumptions. However, it is also nearly exact in cases where the arrival and the service processes are even non-stationary. This shows that the Little's law is very robust in terms of its applicability and is general for uh, and is general under circumstances, certain circumstances. Next. Concluding remarks. We have given a variety of examples showing the kinds of situations where this law is being used in order to convert the estimate of an average queue into an estimate of an average waiting time and vice versa. Within hands-on practice, the operational management and computer architecture has also led its way using the Little's Law. And such developments make the idea easier to implement and help explain why Little's Law have become well known over the last few years. And hence we have come to the end of our video. हाँ, ये last.